The outside main breaker does count as overcurrent protection for the inside panel. NEC section 230.70. A7 states an assembly or enclosure that contains a service disconnecting means and overcurrent protection and that is intended to be used for branch circuit or feeder circuits. NEC section 230.70. A8 states a panel board containing two or more overcurrent devices where there is no protection upstream from the panel board. In this situation, the outside panel serves as both a service disconnecting means and overcurrent protection for the inside panel. It contains the main breaker, which protects the entire feeder circuit and therefore the inside panel. Here's additional information to consider. Firstly, the feeder conductors are sized correctly according to the ampacity of the main breaker. Secondly, the outside panel is properly rated for the ampacity of the feeder and the main breaker. Thirdly, the inside panel is rated for the same ampacity as the feeder and is protected by the upstream main breaker. Therefore, the inside panel is adequately protected by the outside main breaker, and no additional individual overcurrent protection is required. Let's delve a bit deeper into understanding overcurrent protection and its role in electrical systems. Overcurrent protection, or OCP, is a critical safety measure designed to prevent damage to equipment and wiring caused by excessive current flow. This excessive current can result from various factors, including short circuits, overloads, and ground faults. Without adequate overcurrent protection, these conditions can lead to overheating, insulation breakdown, and even fires. There are several types of overcurrent protected devices commonly used in electrical systems, each with its own characteristics and applications. The most common types include circuit breakers, fuses, and ground fault circuit interrupters, or GFCIs. Circuit breakers are electromechanical devices that automatically interrupt the flow of current when an overcurrent condition is detected. They are designed to be reusable, meaning that they can be reset after tripping to restore power to the circuit. Fuses, on the other hand, are single-use devices that contain a fusible link that melts and breaks the circuit when an overcurrent occurs. Once a fuse has blown, it must be replaced with a new one. GFCIs are specialized devices that protect against ground faults, which occur when current leaks to ground through an unintended path. GFCIs are commonly used in areas where there is a high risk of electric shock, such as bathrooms, kitchens, and outdoor locations. When selecting overcurrent protective devices, it is important to consider several factors, including the ampacity of the circuit, the interrupting rating of the device, and the coordination requirements of the system. The ampacity of the circuit refers to the maximum amount of current that the circuit can safely carry. The overcurrent protective device must be rated to protect the circuit against overcurrents without tripping unnecessarily under normal operating conditions. The interrupting rating of the device refers to the maximum amount of fault current that the device can safely interrupt without failing. It is important to select a device with an interrupting rating that is sufficient to handle the available fault current at the point of installation. Coordination refers to the selective tripping of overcurrent protected devices in a system to minimize the extent of the outage in the event of a fault. Coordinated systems are designed to ensure that only the overcurrent protective device closest to the fault trips, while other devices upstream remain closed to maintain power to unaffected portions of the system. The National Electrical Code, or NEC, provides detailed requirements for overcurrent protection in electrical systems. The NEC specifies the types of overcurrent protective devices that are permitted for different applications, as well as the requirements for their installation and coordination. Compliance with the NEC is essential to ensure the safety and reliability of electrical systems. In the specific scenario described, the outside main breaker serves as the overcurrent protection for the inside panel. This is permissible under the NEC, provided that certain conditions are met. Firstly, the outside main breaker must be rated to protect the feeder conductors that supply power to the inside panel. The ampacity of the feeder conductors must be equal to or greater than the rating of the main breaker. This ensures that the feeder conductors are protected against overcurrents that could damage them. Secondly, the outside panel must be properly rated for the ampacity of the feeder and the main breaker. The panel must be able to safely accommodate the current flowing through it without overheating or failing. Thirdly, the inside panel must be rated for the same ampacity as the feeder and be protected by the upstream main breaker. The inside panel must be able to safely distribute power to the branch circuits it serves without being overloaded. If these conditions are met, the outside main breaker provides adequate overcurrent protection for the inside panel, and no additional individual overcurrent protection is required at the inside panel. However, it is important to note that the specific requirements for overcurrent protection can vary depending on the jurisdiction and the specific application. It is always recommended to consult with a qualified electrical inspector or engineer to ensure that the electrical system complies with all applicable codes and standards. Let's elaborate further on the relevant NEC sections mentioned earlier. NEC section 230.70. A7 addresses assemblers or enclosures containing service disconnecting means and overcurrent protection. This section recognizes that it is common practice to combine these functions into a single unit, such as a service entrance panel. The key requirement is that the assembly or enclosure must be suitable for use as both a service disconnecting means and overcurrent protection. This means that it must be properly rated for the voltage and current involved, and it must be installed in accordance with the NEC. NEC section 230.70. A8 addresses panel boards containing two or more overcurrent devices where there is no protection upstream from the panel board. This section applies to situations where a panel board is fed directly from the service entrance without any intervening overcurrent protection. In such cases, the panel board itself must be provided with overcurrent protection to protect it against overloads and short circuits. In the scenario described, the outside panel meets the requirements of NEC section 230.70. A7 because it contains both a service disconnecting means and overcurrent protection in the form of the main breaker. The inside panel, on the other hand, does not require additional overcurrent protection because it is protected by the upstream main breaker in the outside panel. To further clarify the concept of overcurrent protection, let's discuss the different types of overcurrents that can occur in electrical systems. There are three main types of overcurrent: short circuits, overloads, and ground faults. Short circuits occur when there is an unintended connection between two or more conductors in a circuit. This can happen due to damaged insulation, loose connections, or other factors. Short circuits typically result in very high levels of current flow, which can quickly damage equipment and wiring if not interrupted by an overcurrent protective device. Overloads occur when a circuit is carrying more current than it is designed to handle. This can happen when too many appliances or devices are connected to the circuit at the same time. Overloads typically result in lower levels of current flow than short circuits, but they can still cause overheating and damage over time if not corrected. Ground faults occur when current leaks to ground through an unintended path. This can happen due to damaged insulation, moisture, or other factors. Ground faults can be particularly dangerous because they can create a shock hazard if someone comes into contact with the energized equipment or wiring. Overcurrent protective devices are designed to protect against all three types of overcurrents. Circuit breakers and fuses respond to both short circuits and overloads, while GFCIs respond specifically to ground faults. By providing comprehensive overcurrent protection, these devices help to ensure the safety and reliability of electrical systems. In addition to the NEC, there are other codes and standards that may apply to electrical systems depending on the jurisdiction and the specific application. These codes and standards may contain additional requirements for overcurrent protection, as well as other aspects of electrical safety. It is important to be familiar with all applicable codes and standards when designing, installing, and maintaining electrical systems. To summarize, the outside main breaker can serve as overcurrent protection for the inside panel, provided that certain conditions are met. The feeder conductors must be sized correctly for the breaker, the outside panel must be properly rated for the ampacity of the feeder and the main breaker, and the inside panel must be rated for the same ampacity as the feeder and be protected by the upstream main breaker. Compliance with the NEC and other applicable codes and standards is essential to ensure the safety and reliability of electrical systems. Let's now consider some practical examples to illustrate the concepts we have discussed. Suppose you have a 200 amp service entrance panel with a 200 amp main breaker. From this panel, you run a feeder to a subpanel located in a detached garage. The feeder conductors are size 4/0 aluminum, which has an ampacity of 180 amps according to NEC table 310.15. B16 assuming 75 degrees Celsius terminations. The subpanel has a main lug only, or MLO, configuration and is rated for 200 amps. In this case, the 200 amp main breaker in the service entrance panel provides overcurrent protection for the feeder conductors and the subpanel. The feeder conductors are protected because their ampacity is greater than or equal to the rating of the main breaker. The subpanel is protected because it is rated for the same ampacity as the feeder and is protected by the upstream main breaker. No additional overcurrent protection is required at the subpanel. Now let's consider a different scenario. Suppose you have a 200 amp service entrance panel with a 200 amp main breaker. From this panel, you run a feeder to a subpanel located in a detached garage. However, in this case, the feeder conductors are size number 2 copper, which has an ampacity of 95 amps according to NEC table 310.15. B16 assuming 75 degrees Celsius terminations. The subpanel has a main lug-only configuration and is rated for 200 amps. In this case, the 200 amp main breaker in the service entrance panel does not provide adequate overcurrent protection for the feeder conductors. The feeder conductors are not protected because their ampacity is less than the rating of the main breaker. In order to provide adequate overcurrent protection, you would need to install a smaller breaker at the service entrance panel, sized to protect the feeder conductors. For example, you could install a 100 amp breaker, which would provide adequate protection for the number 2 copper conductors. Alternatively, you could upsize the feeder conductors to a larger size that has an ampacity greater than or equal to the rating of the 200 amp main breaker. These examples illustrate the importance of properly sizing the feeder conductors and the overcurrent protective devices in an electrical system. Failure to do so can result in inadequate overcurrent protection, which can lead to damage to equipment and wiring, as well as an increased risk of fire. In addition to sizing the feeder conductors and overcurrent protective devices, it is also important to consider the voltage drop in the feeder circuit. Voltage drop occurs when the voltage at the load end of the circuit is less than the voltage at the source end. Excessive voltage drop can cause appliances and equipment to operate inefficiently or not at all. The NEC recommends that the voltage drop in a feeder circuit should not exceed 3%. To minimize voltage drop, you can use larger conductors, reduce the length of the circuit, or increase the voltage of the circuit. Let's explore the implications of using aluminum versus copper conductors in feeder circuits. Aluminum conductors are generally less expensive than copper conductors, but they also have a lower ampacity for the same wire size. This means that you may need to use larger aluminum conductors to achieve the same ampacity as copper conductors. Aluminum conductors also have a higher coefficient of thermal expansion than copper conductors, which means that they expand and contract more with changes in temperature. This can lead to loose connections over time if the conductors are not properly installed and maintained. When using aluminum conductors, it is important to use connectors that are specifically designed for use with aluminum. These connectors are typically made of aluminum or are plated with aluminum to prevent corrosion. It is also important to apply an antioxidant compound to the conductors before connecting them to the connectors. This will help to prevent oxidation and corrosion, which can lead to increased resistance in overheating. Copper conductors are generally more durable and reliable than aluminum conductors, but they are also more expensive. Copper conductors are also easier to work with and require less maintenance. When selecting conductors for a feeder circuit, it is important to consider the cost, ampacity, voltage drop, and durability requirements of the application. Let's now discuss the importance of proper grounding in electrical systems. Grounding is the process of connecting the non-current carrying metal parts of an electrical system to the earth. This provides a low resistance path for fault current to flow back to the source, which helps to trip the overcurrent protected devices and clear the fault. Proper grounding is essential for protecting people from electric shock and preventing damage to equipment. The NEC specifies detailed requirements for grounding electrical systems. These requirements cover the size and type of grounding conductors, as well as the methods for connecting them to the earth. It is important to follow these requirements carefully to ensure that the electrical system is properly grounded. In addition to grounding the non-current carrying metal parts of an electrical system, it is also important to ground the neutral conductor. The neutral conductor is the conductor that carries the unbalanced current in a 3-wire circuit. Grounding the neutral conductor helps to stabilize the voltage and prevent voltage fluctuations. The NEC specifies the requirements for grounding the neutral conductor at the service entrance and at other points in the electrical system. Let's now consider the role of surge protection in electrical systems. Surge protection devices, or SPDs, are designed to protect electrical equipment from voltage surges. Voltage surges are brief spikes in voltage that can damage sensitive electronic equipment. Voltage surges can be caused by lightning strikes, power outages, or other factors. SPD work by diverting the surge current to ground, thereby protecting the equipment connected to the electrical system. SPD are available in a variety of types and sizes, and they can be installed at the service entrance, as subpanels, or at individual equipment locations. When selecting SPD, it is important to consider the voltage and current ratings of the SPD, as well as the type of equipment that it is protecting. The NEC recommends that SPD be installed in all electrical systems, especially those that serve sensitive electronic equipment. In conclusion, understanding overcurrent protection, proper conductor sizing, grounding, and surge protection are crucial for ensuring the safety and reliability of electrical systems. Compliance with the NEC and other applicable codes and standards is essential for protecting people from electric shock and preventing damage to equipment. Always consult with a qualified electrical inspector or engineer to ensure that your electrical system is properly designed, installed, and maintained.